Okay. All right. To control today for and so forth. You volunteer.
The lady who did it last break.
She's not here.
Oh.
You okay? Just hold this down, but it's very touchy. Yeah. Okay, let's give you a shot.
We should hopefully be back in our regular room on Monday, so
Okay, good.
then we can count ourselves.
All right. Okay. Get set up here. Skype. So I hope today I will have a full and decent quality recording. It's recording now. Okay. Nay, you good to go?
Yep.
Okay. Great. My voice is not working the best today, so we'll see how this goes. But to compensate for that, I have a fresh marker. Okay. Now, where I left off last time, vector norms. And just to review the definition of a p-norm, the sum of the absolute values of all the components of a vector raised to p power, sum them up, and raise that to the 1 over p. And p values for us are p1, p equals 2, p equals infinity. And there's one helpful inequality. Actually, this will be useful to you in the homework that is specific to the 2 norm, so the Euclidean norm, satisfies this inequality. Now, if you've heard of this before, because it comes up in several cases, it is commonly known as the Cauchy-Schwarz inequality. Is that the absolute of the product of 2 vectors is less than or equal to the product of the 2 norms, so it's vectors. Okay. Now, I should point out just I saw this in one book that I've used to help prepare these notes. It is also known as the Cauchy-Bunyakovsky inequality. I'm sure what Cauchy did to be most of the time. Maybe it's the long name. I don't know. Okay. And actually, this is a special case of the Elder inequality. States that the dot product is less than or equal to the p norm of x times the q norm of y, where p and q satisfy 1 over p plus 1 over q is equal to 1. So Cauchy-Schwarz is this Hilbert inequality of p and q both equal to 2. Okay. Yes? Yes. I'm sorry, breaking up down there.
Can you go in a little closer to over?
Oh, do you need the camera moved or?
Yeah.
Yes.
Okay. You need to zoom. Oh, you need to zoom in. Okay.
Yes, that's good.
Okay.
Thank you.
All right. Okay. Now, I actually have a proof of the Cauchy-Schwarz inequality in the notes. I don't really like that proof, to be honest. I just got it out of one of the books that I've used. So I'm going to do a different one that I just find more elegant. Okay. I'm about to pan, or have Patrick, are we good?
Yes.
Okay. Okay. Oh, gotta pan this too. All right. Okay, so the better proof of cauchy source inequality is this. If I consider a vector x minus some constant c times y, so c is any real number, and I'm taking the vector 2 norm of that. Well, for one thing, this norm is definitely going to be greater than or equal to 0. All norms, a norm cannot be negative. But now I'm going to use the, actually going to square this too. So using the properties of the dot product, I can then expand this. So this would be so 2 norm of x squared minus 2c x transpose y plus 2 norm of c squared 2 norm of y squared. And this comes from the fact that the 2 norm of a vector is a square root of a dot product of a vector of itself, but that also can be written as x transpose x. Okay. Now, if we take the expanded version of this, and we think of this as some function of c, it's a quadratic in c. So, if you have a quadratic function, and it's known to be greater than or equal to 0, then what does it tell you about that quadratic function's roots? They could be imaginary, or what's the other possibility? What? Yeah, there's only one distinct real root. So in other words, if we look at the quadratic formula, we have that discriminant, the b squared minus 4ac. And so in order to have only one real root or complex roots, we need, for a quadratic formula, b squared minus 4ac has to be less than or equal to 0. So equal to 0 for a double real root, or less than 0 for complex roots. Now, in this case, I have a is equal to 2 norm of y squared, because it's a coefficient of c squared. B is equal to minus 2 x transpose y, and c is equal to 2 norm of x squared. Now, it's unfortunate that I chose to use c here, because now I'm using c for 2 different purposes. Hopefully that's not causing mass confusion, and remember to use a different letter next time. But you guys are either graduate students or advanced undergrad, so I assume you can keep up. Okay, so I'm going to fill all these into here and see what we get. So B is going to be, we're going to have minus 2 x transpose y squared minus 4 2 norm of y squared, and then 2 norm of x squared must be less than or equal to 0. So now I just work all this out. So I have 4 x transpose y squared minus 4 2 norm of y squared, 2 norm of x squared, less or equals 0. But now I just go ahead and simplify all this. Take a square root of both sides, get rid of a force, and I get exactly the Cauchy-Bonnikovsky Schwarz inequality. Okay. Missed a good part. Okay. What?
That's what it is for.
Ah, good point. All right. I should mention about the video. So what I'm going to do after class, I get this uploaded. If you go to the course website on the lectures page, so under the entry for each lecture, I'm just going to put a direct link to a YouTube video. So just expect that to appear sometime that evening. So I always upload it almost immediately after class, but then I probably have to have them enhance it, like the contrast, so it's easier to read the board, and that takes some time. But definitely by sometime that evening, it'll be up. Okay. Any questions about this proof, which maybe someday I'll put in the notes, about the Cauchy-Schwarz inequality? Okay. Now, so back to the discussion of vector norms in general. Oh, so basically, Patrick. Yeah. So does Pan once I finish erasing? Oh, yeah. Okay. Then people have time to get everything written.
Will you, can you go down and then go ahead and zoom back in again? Because there's a glare, yeah, go down a little bit and then zoom back in. One more time, that's it, thank you.
All right.
I'm done, but I got that.
Okay. Now, so now that we have a notion of magnitude of vector, we can talk about convergence of sequences of vectors. This is going to be important to us for iterative methods for linear systems that we'll get to later. Okay. So if we define a distance between any two vectors in Rn, x and y, it's just going to be the norm of x minus y. Now, we have many vector norms. Notice I haven't specified one here. I haven't put a subscript p or anything. It doesn't, for this discussion, it doesn't matter. It's just some vector norm that satisfies all the properties that any vector norm is supposed to have. So now that we have this notion of distance, we can say that a sequence of vectors that I'll often use this notation for. So for vectors, I'll tend to use subscripts to refer to an element of a vector. But if I have a sequence of vectors like this, I'm going to use a superscript with parentheses. So hopefully it's sufficiently unambiguous. So if I have a sequence of vectors, then, so x0, x1, on to infinity, then we say that that sequence converges to some limit x if we have a following, because we're taking a limit of vectors, but we want to describe this in terms of ordinary limits, limits of sequences of real numbers. So a limit of the norm of xk minus x is 0. So the distance between the vectors in your sequence and your limit is going to 0. Okay. And because of the property of a vector norm, that a vector norm is always positive for any non-zero vector, it turns out that this is true if and only if the limit as k goes to infinity of each component of xk converges to the corresponding component of x. Right. So convergence of the entire vector is equivalent to convergence of, so component-wise convergence for all components, and which is pretty much what you'd expect. And it comes from the fact that a norm is 0 if and only if a vector itself is 0. Okay. Now, so I need to give some justification of why I've not actually specified a norm, a particular norm here. I could choose any norm I want and define this kind of convergence with respect to it. You're never going to have a situation where a sequence of vectors converges to a limit x in one norm that you might choose, say the 2 norm, and then it's going to fail to converge x in a different norm, like the infinity norm. So if you have established convergence of a sequence of vectors in one norm, you're going to have that convergence in all norms. Okay. So for this, to flesh this out a little more rigorously, I need to define the concept of norm equivalence. Because I did an example last time where I give a vector and I compute a few different norms, and you saw the norms are all different. But if a vector is in some sense small in one norm, it's going to be likely small in any other. How? Yes.
That's a question before you go on. So
Yep.
I'm not sure I understand this. So when you say a sequence of vectors, you mean like n x vectors? Is that what you mean?
Okay. All right. So for example, something like okay. So something like xk. All right. All right. So let's suppose we're in R3, and my sequence of vectors is defined by, like, first component 1 minus 1 over k, e to the minus k, and just 0, whatever. So what happens is, as k goes to infinity,
Oh, okay.
this is going to converge to a vector 1, 0, 0.
Okay.
E1. Okay. All right. Okay. All right. So now, so we don't have to worry so much about which norm we're dealing with. We need norm equivalence. So basically, this is what allows you to choose in each situation whatever norm is most convenient. Because sometimes some norm might be more convenient than others. Okay. Okay. So we say that any two vector norms are equivalent if we have actually, I need to define what these norms are. So, for instance, suppose I have a vector norm that I'll call the alpha norm, and another norm that I'll call the beta norm. And so these norms are equivalent if the beta norm of x is bounded above by some constant times the alpha norm of x, and bounded below by another constant times the alpha norm of x. So each norm can be sandwiched in between the other norm times two appropriate constants for all x in whatever vector space Rn that you're dealing with. And, very important, the constants C1 and C2 must be independent of x. Okay. Let's see. Now, all right, so what that means is, suppose you have a sequence of vectors and it's going to 0. The beta norm of these vectors is going to 0. Then it must be true that the alpha norm of those same vectors is also going to 0. There's just no way around it. So it turns out that let's see, how should I do this? Okay, are we good with this board? Okay.
Yes.
So I'm not going over there yet. I'm going to go over here. Okay. All right. So one key statement that I can make about orbitals is that all p norms, so for whatever values of p, are equivalent. So you can use whichever one you want to establish convergence. And now I'll give an example of norm equivalence for two particular p norms. So it turns out that the one norm of x, which is just the sum of the absolute values of the components, is bounded below by the two norm of x. And this is expected because the larger p is, the smaller the norm of the vector is generally. And this is less than or equal to square root of n times the two norm of x. Okay. So the constants in this case, so c1 is equal to 1, c2 is equal to the square root of n. So the constants involved can depend on the dimension of a vector space, n, so for Rn. They just can't depend on x itself. All right. Okay. Now, I can quickly prove this. So if I look at the 2 norm of x squared, so that's just going to be the sum of the squares of the components of x. But that's going to be less than or equal to the sum over all I and j from 1 to n of absolute value of xi, absolute value of xj, because here I just have the terms where the indices are equal, but now I'm lumping in all the terms where the indices are different. But this turns out to be the 1 norm of x squared, because that's the absolute value of the sum of the absolute values of the components, and now I'm squaring that so we get all products of all possible pairs. So this shows that the 2 norm is less than or equal to the 1 norm. So that establishes that the lower bound constant is equal to 1. So I've taken care of this inequality. Now for the other one, okay, suppose I define a vector y. Okay. So I'll define y as follows. Each component is equal to 1 if a corresponding component of x is non-negative, and it's equal to -1 if a component is negative. So, so it turns out that